All right, so let's get started. I'll begin with a simple example just to rehash your definition. Z to the 1 over n, well, not z to 1, excuse me, bad. My bad. We have to be careful to distinguish between z to the 1 over n and the nth root of z. All right, the nth root of z, the principal nth root of z, is a function. Well, it's a single-valued formula, let's say that at the moment. This is equal to the nth root of the modulus of z times e to the I arg of z over n. All right. Furthermore, omega sub n is equal to, and I'll write it this way, exponential of, oh, that's why I hate this board, I forgot, 2 pi I. Oh, I forgot. This thing squeaks. You knew that. Dang it, I forgot. All right, e to the 2 pi I over n. This is the principal nth root of unity. All right, so, and the z to the 1 over n, you could write as, well, it's the nth root of z, right, comma, omega n nth root of z, omega n minus 1, excuse me, omega n to the n minus 1, nth root of z. These are all the solutions of w to the n equals to z. Now, of course, there's an easier way to write this. You could write that as just like the nth root of z times 1 omega n squared omega n to the n minus 1. Like that way you don't have to keep writing this over and over again. So if you're asked a problem like this, you want to write your answer like more nicely, it's kind of nice to just pull out the nth root and then write it like this if you wanted. Example, I'll just look at the 5th root of z. This would be e to the 2 pi I over 5. I'll tell you, we'll look at the 5th one, e to the 2 pi I over 5. And so, of course, that's cosine of 2 pi over 5 plus I sine 2 pi over 5, you know? And I can graph those. So like 2 pi over 5 is 360 over 5, which is what, in terms of like degrees? 360 degrees divided by 5 is, 72, I think. So it's round about here, and then you go another 72, you're like over here, and then you're like over here, and then you're like over here, and then of course you got here. So these are the 5th roots of unity. So these blue dots form 1 to the 5th. There's these 5 things, omega, omega squared, omega 5 cubed, omega 5 to the 4th power, and then of course omega to the 5th, omega 5 to the 5th power is just 1 again. So these 5th roots of unity, they're on the unit circle, right? And for what it's worth, they do come in conjugate pairs. If you added together all of these, you'd get 0, right? They're symmetrically situated about the origin, so that if you were to just take their sum, you know, omega 1 plus omega 2 plus omega 3 plus, I'm an idiot, omega 5 squared plus omega 5 cubed plus omega 5 to the 4th power plus omega 5 to the 5th power, you get 0. Because they're symmetric about the origin, and so like their average is the origin itself. What more can you do with these? Well, one nice thing you can do, so these solve z to the fifth equals to 1, right? Every one of these is a solution of z to the fifth equals to 1. So that means that they solve what? They solve z to the fifth minus 1 equal to 0, right? So you can factor z to the fifth minus 1 as z minus omega 5 times z minus omega 5 squared, z minus omega 5 cubed, z minus omega. I'm starting to regret writing the sub 5 on this example, right? A smart thing to do if you're working a specific example is just to let omega 5 equal omega for the context of the problem, you know? But there it is. So we can factor polynomials sometimes using these roots of unity, all right? Complex polynomials. All right. So in my notes and also in Gamelin, of course, he talks about a little bit about something called stereographic projection and the extended complex plane. We'll come back to that when we have more need of application of it. I'm going to skip over it for now. That brings us to section 1.4, which is on the square and the square root functions. So let's see here. So we need to define a couple things. One is that, well, the first thing I should define before I even define this is that we, in the complex, we'll use the following notation. If we've got z1 comma z2 like this, what this means is the set z1 plus t times z2 minus z1 such that 0 is less than or equal to t is less than or equal to 1. That won't come off. So in other words, this is our notation. This is not an interval. It is a line segment from z1 to z2, okay? So that's a convenient notation for us. And, you know, we also have more general meanings, like if we wrote 0, or like say 0 included to infinity, what that would mean would be things of the form, you know, like basically t, such that t is greater than or equal to 0. So we can view that as a subset of the complex plane, right? Right, so like if I wanted to picture this one, where would this 0 to infinity be in the complex plane? It's the positive real axis. Yeah, it's this thing here, right? So standard notation, you can talk about the positive slit plane, and so C plus is C minus this set. So basically, it's everything except for that red line, that red ray. That's a, no, that is a thing I can't erase. Well, maybe. Aha. It's okay. I don't have COVID. And then also we have C minus, which is C minus minus infinity to 0. All right, so I usually draw a picture of that like this. I just say, okay, so I'm basically taking everything and I'm just getting rid of that. So the corresponding, I usually draw the picture, you know, to say I'm deleting the positive x-axis here. I usually do a d, saying it is forbidden. But this is the positive split plane. All right. So let's study f of z equals to z squared, all right? For, what is it?
No, it's just notational, so you can just use, we call it C minus when we go with subtraction, and we call it C plus when we go with the positive sign.
Yeah, so it's C plus is missing the positive axis, C minus is missing the negative axis. They're sort of negative labels, if you will. So we can study the square function, right? And let's see what happens if we, say, just look at well, let's see what happens if let's look at it in terms of polar coordinates, right? So suppose we have f of, r e to the I theta, right? What happens? We get what? We get r squared e to the 2I theta. So we're like doubling the angle, right? So often it's useful to visualize what a complex function does in terms as a mapping. So we start from the z plane and we go over here to the w plane, all right? And so, for instance, we could suppose that 0 was less than theta was less than pi, right, in our domain. So what would that be?
90 degree, 180 degree plane.
Yeah, let's see here. Where would what would this be geometrically if theta is the standard angle? It's the what?
Top half.
The top half, right? That's the upper half plane, right? Like that. And so if 0 is less than theta is less than pi, so this is equal to w, right? We think of this as being f of, so here we have f of z equal to w. So in this case, w is equal to z squared. So over here, we have what? This is our w. What can you say about the angle there? Well, you've got, basically the angle over in the w plane is twice what it was. In fact, we have, so if we wrote w is equal to like s e to the I beta, you could see that we have 0 less than 2 theta less than 2 pi, right? And that is 0 less than beta less than 2 pi. In other words, the image of the square function takes angles in the w plane that go from 0 to 2 pi. We started with 0 to pi in the domain, but the range, right? The range ends up going, see, where is it mapping?
Anything that's not that one.
Right. So if I call this upper half plane, say u, right? Then what I have is that f of u is equal to what? It's equal to the well, it's the slit complex plane, isn't it? It's C plus. So what would the inverse function be here?
Well, you have to map it from that split back to the upper half.
Yeah, what's f inverse?
Well, you take any squared and you just pull 2 out.
So yeah, f inverse of w, right? would be f inverse of the, the modulus of w times e to the I beta, right? Yeah. And we would just write, square root of the modulus of w, e to the I beta over 2. And this is for 0 less than beta less than 2 pi.
Okay, so the inverse function actually has a longer domain, a bigger domain to work with that you can put into it.
In this case, yeah. Well, certainly the angles we have to think about for the domain of the inverse function are more than the angles for the domain of the square function in this case, because if we took the whole plane in the domain, when we square it, we won't cover the complex plane once, we'll cover it more than once. We've almost covered, well, to be fussy, do you include the real axis on the half plane or don't you? If you included the real axis, either half of it, either the plus or the minus, you'd cover the whole complex plane. All right. Anyway, the question though is, so there's the formula for the inverse, right? Is that the principal nth root of w? Well, it's not, right? Because the principal nth root of w is defined how? It's defined using the principal argument, right? And the principal argument assumes that the angle is where?
0 to pi. No, negative pi to pi.
Negative pi to pi, pi included, right? So if we define let's see here, arg alpha of z is equal to theta such that z equals to modulus of z e to the I theta, where theta is an element of, let's say, alpha minus 2 pi comma alpha, then we could write this as like the square root of the modulus of w times the exponential of I over 2 arg 2 pi of w. Because that would be assuming that the angle that it's taking from the complex number is ranging from 0 to 2 pi.
Yeah, and so when you subtract 2 pi, it gives you back.
Yeah. Now, in the notes, I've defined arg alpha slightly differently. Like, for me, when I first wrote my notes, I made arg alpha go from alpha to alpha plus 2 pi. All right? And let us just come to the following understanding. You can define arg alpha to mean whatever you want. But just define it at the start of your problem and work with it, okay? Don't, there's a problem in Mission 2 that I need to talk more about, because there's anyway. I was thinking maybe it might even be better to define it this way, like arg sub I of z equals to theta, such that z is equal to, modulus of z e to the I theta, where theta is an element of I, all right? With the understanding that I is some interval of length 2 pi, half open, half closed interval from length 2 pi that you're taking angles from. The reason we don't want to include, we want it to be a unique set of angles, so like we don't want to double count 0 and 2 pi. So it's important that that interval be either half open or half closed. But there's some problems that make it natural to include the upper angle, and there's some problems that make it natural to include the lower angle. So you really want both in your, you want to be able to do both. All right, enough about this. So let me I will warn you. I think example 1.4.3 in my notes. I don't think it's. I'm not sure it's wrong, but I don't like the way it's worded. And I have a handout where I talked a lot more about the inverse function idea for the like the square function. So I'm going to try to find that handout and post it so you guys have something better to read. Like the principal problem with what's in the notes is it's missing a picture. And like it's very important to have a picture to guide your thinking when you're talking about how to find the inverse function for a power function. So
the big point here is that you cannot define them as the same thing. Principal and the inverse function of the inverse power function.
yeah, it depends on, well, it depends on how you, let's see, I guess this is example 2. If we have f of z equal to z to the power n, let's say for n greater than or equal to 2, right? And you basically let's take the domain to be like, this, 2 pi over n minus 2 pi over n. So, for example, in n equals 2, in this setup, the domain of my nth power function would be the c minus, because 2 pi over n would just be pi, so it would be just, so n equals 2 gives u equal to c minus, okay? So let me do some shading here. So, all right, so I'm saying that this sector is U, okay? And if we look at f of, z equals to z to the n, well, let's look at modulus of z times e to the I theta, right? To the n, we get modulus of z to the n, e to the I n theta. So notice that minus 2 pi over n less than theta less than 2 pi over n gives us that minus 2 pi, gives me, oh, my bad. I don't need a 2 there. Sorry, so sorry. I just meant minus pi over n. Wait a minute. No, I need a 2. One second here. Let me think through this for a second. Yeah, just pi, All right, and then, okay, so I start with minus pi over n to pi over n. I feed it to the nth power function. It gives me images that look like this, right? So if you think about that, then if I multiply this through by n, I get minus pi less than n theta less than pi, right? So if we have w equals to, modulus of z to the n e to the I n theta, and think about that again as like w e to the I beta, you can see that beta has what, minus pi less than beta less than pi. In other words, if I visualize this map here as the z-plane, and I take it to the nth power, over here, what do I have? What's my image? I have a half plane. I'm missing pi and minus pi, right? Otherwise known as, but the negative real axis, right? I'm missing this. So the image here, this is, W plane. But what we have here is this sector mapped to everything, right? Except what? Right, so in short, f of u, in this case, was just equal to c minus. And it is with respect to this restriction of the nth power function that the principal nth root is the inverse. See? So like f inverse would go the other way, right? So here, f inverse would be a mapping from C minus back to the sector, which I'll call U, by f inverse of W would just be the principal nth root of W. And that makes sense, right? Because this is the nth root of the modulus of W times e to the I arg W over n. And so if you think that through, that makes sense because the argument of W is between minus pi and pi, not included. And when you divide that by n, what do you get? You get from minus pi over n to pi over n. So the angle of the formula here, right, this angle, it maps to this sector like you want. And you can actually compose these functions and show that you get the identity, right? Like here, I'll do it. F of f inverse of W is equal to the nth root of modulus of W times e to the I arg W over n, right? To the nth power, which is the nth root of the modulus of W to the nth power times e to the, I arg W, which is just modulus of W times e to the I arg W, which of course is just W again. And the fussy thing here, again, is to notice that the I mean, you might say, well, why can't you just use like, a different argument? Well, if you use a different argument function, then when you divide by n, you get a different sector back here. So anyway, you can choosing different arguments for the for the nth root function corresponds to like moving this sector different places. Anyway, I don't want to say more about that because I think this is a good place to stop here for this discussion. So I'm going to just stop right there. All right. Okay, so next I need to define for you our typical elementary functions, and I'll try to be, I'm going to start by just telling you the definition for each of the functions, all right? And then I'll stop and I'll talk more about their properties, okay? But I want to make sure I at least give you the definition for all the elementary functions before we go on. So first of all, e to the z, all right, which is e to the x plus iy, is going to be e to the x times cosine y plus I sine y. So that's the definition of the exponential function, all right? So basically, we're just extending the Euler's identity that we already did by multiplying it by e to the x, all right? We also can define cosine of z. Cosine of z is going to be 1/2 e to the iz plus e to the minus iz. So you remember we had that formula where theta was a real number. We're just saying, hey, you know what? We're going to use that formula when z is a complex number. That's going to define cosine for us, at least for now. There are, of course, more sophisticated definitions of sine and cosine that we can offer later when we have, you know, more analysis at our disposal. But for now, this is a good temporary definition. But it is our definition. So sine of z, 1/2i e to the iz minus e to the minus iz, that's sine. There's also hyperbolic cosine. 1/2 e to the z plus e to the minus z. This is our hyperbolic cosine. Hyperbolic sine, 1/2 e to the z minus e to the minus z. All right. That's our hyperbolic sine, hyperbolic cosine. It's striking how similar they are, right? In terms of their formulas. And that's part of the reason we call hyperbolic sine and cosine hyperbolic sine, hyperbolic cosine, all right? These are all z's, except for the 2's. These are 2's. Make my 2's loopy. There we go. Loopy 2's. There, it's safer. And then you've got more. I don't know if there's even any homework on these just yet. I'm just throwing them out there. These are functions we can play with, all right? So the log of z, all right, is defined to be the natural log of the modulus of z plus I times the principal argument of z. This is how we take the logarithm. And again, we're assuming for z not equal to 0. All right. Now this is the principal logarithm, and it will define an inverse for a particular restriction of the exponential function. All right. So we'll look more at that when we have time here. What else can I tell you here? I should mention, so these are elementary functions. All right, so let me talk to you about some multiply valued functions. And I put functions in quotes because what's the fundamental thing about a function? It's what? Single valued, right? So what do you mean multiply valued function? But here it is. Log, little log of z, is natural log of the modulus of z plus I times arg. Remember arg z? That was the set of all coterminal angles describing z, right? And so likewise, little log z is a set of values. In addition, if we take z to a complex power, that is a set of values. And let's see here. What would that, how do you think we're going to define that set of complex values? Well, here's how we do it. Basically, we just say, well, that's going to mean the exponential of c times the log of z. And if you wanted to talk about like the principal seeth power, you could just replace this little log with a big log. Then its domain would be the slit C minus plane. Okay, like the domain, you notice that the domain of the logarithm, I should really mention that. Well, here's the thing, is if you want, well, I'll just say this, can use C minus as domain. But if you do that, then this function's discontinuous at the slit in the plane. I mean, if you use the domain as the punctured plane, as just C with an X, then the logarithm is not a continuous function because like it jumps at the slit in C minus because the angle there jumps from minus pi to pi. It's not continuous. Okay, anyway. Let me not get too sophisticated here just yet. Let's actually look at how to calculate the logarithm of a complex number. Yeah. So, questions that one of the things you want to do, in terms of all these elementary functions, is understand how they behave as mappings. Like, if we put W equals to any of these formulas, what happens? What happens in the W plane? So we'll get to that. But before I get to that, let me just do some basic calculation here. What example am I on? 3. What is the log of 1 plus I? Let's see here. So it's the modulus of 1 plus I, right? Plus I times the argument of 1 plus I. What is 1 plus I? Well, you know the deal, right? 1 plus I is here, right? So it's pi over 4, and yeah, root 2. So the answer is square root of 2 plus I times pi over 4. This is the principal log. The set little log, so the set of all values of the log, 1 plus I would be, square root of 2 plus I pi over 4, right? Plus, let's see here, 2 pi I z. I can make it more explicit here. So what we're looking at really is square root of 2 plus I times pi over 4 plus 2 pi k, right? Such that k is an integer. Like there's a more, if you don't know what I meant by what I wrote above, that's what I meant. It's all those values. It's sometimes helpful to notice like the formula in terms of x and y. So like log of x plus iy. It is, what is it? It's the natural log of the square root of x squared plus y squared, right? Plus what? Oh man, there is a typo in my notes. So definition 1.6.2 is incorrect. I just have plus iy here, which is not right. It's plus I times the argument of x plus iy. What is the argument of x plus iy? It's complicated. You got to find the standard angle of that, right? So if you happen to be in quadrants, you know, yeah, I'm trying to think, 1 and 2, I think it's just inverse tangent of y over x. Try to decide whether that gives me the proper values. Yeah. Well, what I'm saying is, if I use inverse tangent here, right? This is automatically between minus pi, you know, less than, actually pi over 2, right? So is that an appropriate angle to be a principal argument? Well, remember, principal argument where? Yeah, the range of arg is minus pi not included to pi included, right? So in that context, right, if we're in, so the words, this, golly, let's do marker. So this is, if you have z here or z here, you know, in quadrants 1 or 4. In other words, if the real part of z is greater than 0. If the real part of z is greater than 0, if you're in quadrants 1 or 4, then yes, the formula for the principal logarithm, you can be given by, you know, the natural log of the square root of x squared plus y squared and plus I times inverse tangent of y over x. But if you want to find the formula for the standard angle in quadrants, you know, 2 or 3, well, you got to either add or subtract pi or something as appropriate, you know? Okay, so example 4. This would be a really short example. What's the log of minus 3? See, this is the log of 3 e to the I pi, right? So this is natural log of 3 plus I pi. So we can take the logarithm of a negative number in complex analysis, just that the answer is imaginary. So to be logically complete here, I really should show you that the exponential and the logarithm are inverse functions, right? But I'm not gonna I'm not gonna do that at the moment. I think I'm gonna continue showing you examples of how these things work, yeah, for the moment. Let's see here. Let's see here. So, let's talk about example 5. I to the I. So by definition, this is supposed to be what? This should be exponential, right, of, let's see here, in this case, c is I, right? So I log of I.
Can we write that as like e to the...
Now, let's see here. So I is equal to e to the I pi over 2, right? So log of I is the natural log of 1 plus I pi over 2. In other words, it's I pi over 2, because natural log of 1 is 0. So this gives us that I to the I is, what is it? It is exponential of I times, oh, I'm sorry here. I just calculated this is big log, isn't it? My bad, sorry. So I times what? Times, no. The I to the I is part of this down here. So this is a multiply valued function. It's a whole set of things. So you could think about the principal cut of the I to the I function or the Z to the I function or something. But anyway, so this is I pi over 2 plus, 2 pi I Z. See, because little arg of Z is equal to big arg of Z plus 2 pi Z. We just add all multiples of 2 pi, all the coterminal angles form the arg. So I can just, again, log I here is what this is the set that's log I. It's I pi over 2 plus 2 pi I over Z. Because you get I arg Z in this, so that I multiplies the 2 pi Z. So what is this? Well, I'll write it explicitly. This is things of the form e to the, let's see here, what do we got? I times I is what? Oh, check it out. I can factor the I out, right? So I just get minus parentheses pi over 2 plus 2 pi k such that k is an integer. So I to the I power is actually a set of real values. Right? Yeah. Here's a quote from a letter to Goldbach from Euler, written in 1746. Recently, I have found that the expression square root of minus 1 to the square root of minus 1 has a real value, which in decimal fraction form is approximately 0.20787957763. This seems remarkable to me. So, yeah, Euler was doing this back in 1746. Now, he said one of the values. He kind of knew that there was more than one value, but he said this is a value of it, So, now, of course, you could define the, if you wanted to define a principal value of Z to the I, you could just use something like exponential of I log of Z, right? And that would pick one of this infinity of choices for the outputs, because we just basically be putting k equals to 0 in this, so. But of course, there's no, anyway, the notation leaves something to be desired. You kind of have to write in words, I'm using this branch or something. Okay. I wanted to show you that. Oh, man. Time flies when we're having fun, doesn't it? So, do you have time for me to do one more thing? Yeah. Do you have another class right now? Yeah. Okay. So, just one more thing for today. Let's talk about how e to the z maps. So we have e to the z, right? is equal to, e to the x plus iy, which is equal to e to the x times cosine y plus I sine y, right? And so sometimes it's helpful when you're trying to study the mapping to see what happens to given things in the z-plane as they map to the w-plane. Like, so here's z-plane, and over here will be the w-plane. So, and this is my function f of z equals e to the z, all right? So one thing we could do would just be to look at x, like a vertical line, right?
Yeah.
So, x equals to x naught. What does that map to? So if we look at something, so this would be, to study it more explicitly, you can parameterize the line. So that red line has parameterization, something like, what is it? Well, x naught plus basically it, right? Because typical point on here is like x naught plus it, where t is a real number, whatever. And what happens to that when we feed it to the exponential function, we get e to the x naught, e to the it actually, right? And so this, of course, is cosine plus I sine t, right? But what that does is it gives you, this is on a circle, radius e to the x naught. And then as t varies, you just go around the circle. Round and round and round she goes. So it's actually, whatever that is, there's a circle. And how many times does it cover that circle? Infinitely many times, right? Unless you did what? Unless you you'd have to, if you limited the t to go between, a particular set of values, then you can make it just cover the circle once, right? So to make the exponential function one-to-one, we're going to have to restrict to a horizontal band, which isn't too big. Otherwise, we get,
So essentially anything from 0 to the end of the circle.
Yeah, like the traditional one is just to go between, say, minus pi, pi and minus pi.
Yeah, you couldn't go all the way to the completeness of the circle, right? Because that would make it not.
Well, if you included one of these, yeah, that's true. You wouldn't get one-to-one. That's right. But if you include, well, if we exclude both of the minus pi and pi, what are we going to be missing? We're going to be missing this right here, right? And what happens if you take, a different x naught? Well, right. So, as you get over here, x1, then you're getting closer and closer to the, right? And as you take the lines farther and farther out, right? And I'm assuming that, assuming we just take we only use, let's change our original setting to just to go from here to here, then we get these almost circles, right? And so if you were to restrict the exponential function to just this horizontal strip, right? Then the image of the exponential function would be the slit complex plane, C minus.
Oh, okay, yeah.
So if we let u equal to z,
You make infinitely many circles that just keep going and going.
yeah, so z such that minus pi less than the image of z, imaginary part of z, is less than pi, all right? Then f from u, it goes from u to c has f of u equal to c minus. And in fact, f inverse is the principal logarithm. So f inverse from c minus back to u is given by f inverse of z, or you could say f, I've even been using w here. So f inverse of w equals to principal log of w. And that's a good formula because it doesn't have the jump inside its domain. The place where the angle jumps is outside. It's this where the slit is for the principal logarithm. But, and then of course the other question would be like, where do horizontal lines go? So if you look at a horizontal line, yeah, so like y equals to, you know, pick whatever you like y equals to pi over 4, where does that go? So to figure that out, you do something like f of, you know, t plus I pi over 4, right? Which is e to the t square root of 2 over 2 plus I root 2 over 2. In other words, that is that's basically just this, see? The origin's deleted and it's just this ray. This is a ray at theta equals to pi over 4. So horizontal lines get mapped to rays, vertical lines get mapped to circles under the exponential function. But anyway, these are the things that we have homework on to wrestle with. I can't do all of it in lecture, but we'll come to an understanding of what the exponential, the logarithm, all these different functions are as we work problems on them. So anyway, next up, we start to talk more about analysis. So these, I have introduced to you the basic players of the game, and now we will start playing the game. There is much more in my notes than I have said in class. I would encourage you to read. So, thanks.